Good morning, everyone, and welcome to the August 2023 edition of the Southeast Monthly Climate Webinar, where we talk about the climate and special topics pertaining to the Southeast region. My name is Chris Furman. I'm the regional climatologist with NOAA's Southeast Regional Climate Center, and I'll be giving a climate overview of the past month. Our other speakers today are Jeff Dober from the Southeast River Forecast Center, who will provide a water resources update, Dave Zierden from the Florida Climate Center, who is filling in this month for Pam Knox and will provide an agricultural impacts update. And this morning, we're very pleased to have Jacob LaFontaine from the USGS South Atlantic Water Science Center, who will be discussing future water availability and streamflow characteristics in the Southeast United States. So again, thank you all for joining us. Just a reminder to type your questions and comments into the question box at any time, and they'll be answered at the end. Also, a recap email of this webinar will be sent out with a YouTube link to the recording in the next day or so. All right, so we'll get started with an overview of the climate. Next slide. So in terms of temperature, over the past month, we saw essentially a continuation of the same pattern that we discussed last time, with the interior of the region running a bit below average and the southern and eastern portions of the region running above, and in some cases much above average. Several locations across Florida, including Key West, Fort Myers, Miami, Tampa, Sarasota, Punta Gorda, and others, all recorded their warmest month on record back in July. And more records may be broken again this month. Record warm water temperatures in the Gulf of Mexico have also contributed to high humidity and record-breaking overnight temperatures. Just a few weeks ago, the temperature in Key West dropped to just 88 degrees Fahrenheit, which is the highest minimum temperature in a record going all the way back to 1872. The heat also continued across the Caribbean, where several locations remain on track to record their warmest summer on record. On the other hand, a few long-term stations in central and western portions of Virginia and the Carolinas, as well as in eastern portions of Tennessee, are actually on track to record one of their coolest summers on record. So definitely a tale of two temperature patterns across the region this summer. Okay, next slide. Looking at precipitation, again, as is typical during the summer, we see a good bit of variability across the region here over the past 30 days. It was rather wet across the state of Tennessee, as well as across a good portion of Georgia, northern Alabama, and eastern Florida. On the other hand, rainfall deficits continued to build along the Gulf Coast, while dry conditions reemerged across Virginia and especially across eastern sections of North Carolina. This is reflected in the most recent drought monitor maps, which we'll look at on the next slide. Rainfall has also been variable across the Caribbean, though year-to-date deficits are still notable across the Virgin Islands, where St. Thomas is off to its fourth driest start to the year with only about half of its expected rainfall, while St. Croix has recorded only about 2/3 of its expected rainfall so far this year. Okay, next slide. All right, so looking at the drought monitor, we see improvements across Tennessee and northern Alabama due to the recent rainfall. But warm temperatures and lack of rain have led to an emergence of abnormal dryness across the northern Gulf Coast and across eastern portions of North Carolina, with some moderate drought emerging near the mouths of the Pamlico and Neuse rivers. Pockets of abnormal dryness also emerged across parts of Georgia and South Carolina, while moderate drought continued to persist across northern Virginia. In addition, the I-75 corridor between about Tampa and Fort Myers has seen at least a 1-category degradation over the past month, with severe and extreme drought emerging across parts of Hillsborough, Manatee, and Sarasota counties. Nevertheless, overall drought coverage actually remains at one of the lowest percentages region-wide over the past 2 years. Okay, next slide. So looking in the Caribbean, we see the reemergence of severe drought across the northwest part of Puerto Rico, with some abnormal dryness persisting in the same areas over the past month or so. Conditions on St. John improved a bit from severe to moderate drought, while extreme drought persisted on St. Thomas and St. Croix, and this, of course, reflects the long-term drought conditions there on those islands. Okay, next slide. All right, turning to ENSO, the August update from the Climate Prediction Center indicates increased confidence, now about a 2 in 3 chance of a strong El Nino event by this winter, based on observed and forecasted sea surface temperature anomalies, which have increased a good bit over the past several weeks. We're also seeing a bit more of a coupling of the ocean and atmosphere, including an uptick in westerly wind anomalies across the equatorial Pacific. However, it's important to note, and the CPC stresses, that a strong ENSO event doesn't always mean significant impacts locally. So we still need to keep an eye on shorter-term weather conditions and climate patterns. Okay, next slide. So looking out over the next 3 months, as we turn our seasonal calendars to fall, we see that the CPC continues to forecast above average temperatures across the region with a slightly higher probability across the southern tier, while above average precipitation is projected for virtually the entire region. Next slide. If we look across the Caribbean, we see the NMME ensemble is projecting above average temperatures and above average precipitation for the Caribbean region over the next 3 months. Okay, next slide. All right, looking at the seasonal drought outlook, no real change actually from last time. Drought removal still remains likely across the region, with improvements expected across the Caribbean, and no new development is expected. Okay, next slide. Earlier this month, the National Hurricane Center updated its seasonal outlook for the Atlantic Basin. Of note, the NHC increased the likelihood of an above average season from 30% to 60%, while the likelihood of near average activity, which is around 14 named storms, has decreased to 25%. As you can see in the graphic here, the NHC is now calling for as many as 21 named storms. Recall their May forecast was for as many as 17. 6 to 11 of which could become hurricanes, and 2 to 5 of these could become major hurricanes, which is category 3 and higher. More information on this updated forecast can be found there at the link at the bottom of the slide for you to look at after the webinar. So far this season, there have been, well, now I guess 9 named storms in the Atlantic Basin, one of which became a hurricane. That was Dawn. So we're a bit ahead of schedule in terms of the number of storms. And while the accumulated cyclone energy was a bit above average to start the season, it's now about at its climatological value. Okay, next slide. Okay, so this is out of date. This is from last evening, but the National Hurricane Center was monitoring several areas of activity and still is across the basin. Most notably for our region, some rain bands connected to Tropical Storm Franklin have been dropping rainfall across Puerto Rico since yesterday, and there is the threat of flash flooding and landslides, as well as gusty winds and rough surf. A disorganized cluster of thunderstorms associated with a tropical wave is currently located west of the Cabo Verde Islands, and there's a decent chance that it will develop into a tropical cyclone over the next week. We'll need to look at this map again soon, because again, this is as of last night, so this has probably changed some here this morning. Okay, next slide. Okay, so for the rest of the month, temperatures are expected to remain above average across the southern half of the region, while temperatures are actually leaning below average across the northern tier. In terms of precipitation, the western half of the region is leaning below average, while the eastern half is leaning above. Next slide. And that pattern is more or less reflected in the 7-day QPF. This is from yesterday evening, where some locations from northern Florida up into eastern Virginia and across South Florida and the Appalachians could see over an inch of rain. But total rainfall is expected to be less than a quarter of an inch across much of the rest of the region. Okay, next slide. Looking out to 2 weeks through Labor Day, we see a continuation of warm weather across the southern tier of the region, with cooler than average weather across parts of North Carolina and Virginia. Precipitation is forecasted to remain below average across, again, the western part of the region, and near normal to above normal across the East Coast. Next slide. And then if we look out 3 to 4 weeks, this takes us to about mid-September. We see above average temperatures covering the entire region, with equal chances of either above or below average precipitation, except across parts of western Tennessee, where precipitation is leaning above average. Okay, next slide. Should be the summary. Yep. Okay, so thank you very much for your attention. Here's the summary for you to look over after the webinar. Happy to answer questions at the end. And with that, I'll turn it over to Jeff.
Alrighty, thank you, Chris. And Chris gave you the climate and weather rundown, and we're going to talk about how that's affected stream flows and what we're expecting as far as stream flow into the future. And so we always start off with showing our USGS maps here, provided by the U.S. Geological Survey, who you're going to hear from Jacob here at toward the end of the meeting. But so you can see there a lot of green dots across the entire southeast showing near normal conditions. as far as stream flows. And this is sort of what we've been talking about all summer, is near normal stream flows. And so we're continuing to see that in most locations. There are some pockets of below normal you can see there, which match up well with Chris's rainfall map that he showed earlier, namely across eastern North Carolina, parts of the Gulf Coast region, as well as the Tampa area on the West Coast there. As far as the 28-day duration hydrograph there on the right side, we've been near normal for a good, we talked about this the last time, near normal, in the near normal range as far as stream flow across the Southeast, really for the last couple of years, only going in the above normal and below normal for some short periods, but for the most part in that green range. Breaking it down by each state, we'll go to the next slide here. And we can see in Alabama, Georgia, and in Florida, that black line there showing near normal conditions for all three states. And if we move east, that's near normal as an average. If we move east into the Carolinas and Virginia, again, the trends continue, near normal conditions as far as stream flows across those areas as well. So what are we looking at into the future? If we go to the next slide, and we'll show you, here's the current river conditions. And for the most part, we've got all of our river gauges reporting below flood levels or below high water levels. We do have some high water down there in the Santa Fe River Basin in the North Florida. That's that yellow square there, as well as down across some of the South Florida areas, including Lake Okeechobee. Some recent heavy rains have brought some of those stream flows up, but for the most part, below flood conditions across all our areas, Southeast as well as Puerto Rico. We go to the next slide, and we'll show you the river flood climatology as we always do. We're in week 34. Again, this is still remaining in the summer quiet period. And if we go to the next slide, there's one exception with this, and that's in the Florida Peninsula, where we ramp up during the wet season. But this wet season hasn't been as pronounced. As Chris pointed out, we've had a little bit of less rainfall on the West Coast this year. And so we're not seeing that reflected in the stream flows as much, and haven't really had the flooding that we typically see down there in the month of July and then the August. But the tropical season is still, the peak of the tropical season is still approaching. And if we go to the next slide, we can show that. Again, about 1 in 9 storms in the Atlantic Basin have an effect on the Southeast and produce widespread heavy rain. So with potential 20 storms, we still have potential to see that one of those storms in the Southeast, and this reflects that here. This is the Southeast tropical storms region, the number of tropical storms by region by week of the year, and we're in week 34. Usually week 35 through 39, as you can see in the data, there is more active weeks. And so we're moving into that period here, and we'll see how that works out. But that, of course, will definitely affect stream flows if we see a tropical system. And if we can go on to the next slide. And so all in all, we're going to continue that trend. The stream flows have continued to be mostly in the normal range from really the beginning of the year through the spring and summer months. And we're going to continue to play on this trend through the remainder of the summer into the autumn. Now, the exception here is as we move into late November, we'll maybe see more of the effects of the El Nino, the moderate to strong El Nino that Chris had talked about. And this could start to enhance some of our rainfall and potential stream flow. And this is based on some of the analogs that we've done in the past. If we go to the next slide, we can see that when we do have El Nino conditions, stream flows there's a good chance that stream flows are in that above or at least in the near normal range. You can see the actual pie charts, the shaded green area in the southeast there. Less chances that we'll see below normal stream flows. So better chances of above and near normal when we have El Nino. So that plays on our forecast. And that plays on our last slide here as we show the summary. Again, 28-day U.S. Geological Survey stream flows are all mostly near normal. And we're going to continue to see that near normal forecast through the remainder of the summer and early fall. Of course, tropical activity is always a caveat, and we're entering the most active period here for the month of September. The Southeast usually on average, usually at least sees one tropical system, named tropical system to affect the Southeast every September. So we'll at least see one. Whether it'll be a heavy rain event or not, we'll have to wait and see. So that's what we're looking at. And then as we go in toward the latter half of November and into the end of the year, then we'll start to see maybe the effect of the ENSO start to play on stream flow, rainfall and thus stream flows. So that's all I had as far as water resources and flood potential. And I will pass it back to potentially David if he's here, or Chris.
Hi, Chris, this is going to you.
Okay, sounds good. All right. Well, we'll go ahead and get started, and we'll look at some of the ag impacts here across the region here over the last 30 days or so. So we talked about some areas that have gotten some rainfall over the last month or so, and that's certainly helped keep moisture levels pretty good in places, despite the fact that it's been rather warm. Tobacco harvest ahead of historical levels, and a lot of that certainly is due to favorable conditions. However, the humidity and heat continues to cause an expansion of fungal diseases. We've been talking about this now for some time. So white mold, algal diseases on things like blueberries and other vegetables, that's been a concern for farmers as they've been trying to kind of keep ahead of that by spraying. Livestock producers have really been keeping track of the high heat and making sure that their cattle have adequate shade and water. That's been another area of focus here over the last couple of months. Some farmers are now beginning to treat sun scalding on vegetables. And as we talked about before, the recent heat and lack of rain has also caused dry conditions to expand across parts of North Carolina and Virginia, and we're maybe going to start seeing impacts to ag and water resources down the road. Corn that was planted early has been harvested, and the yields look pretty good. Corn planted a little later, they're expecting some lower yields due to the dry conditions that we experienced during the pollination stage. Okay, next slide. If we look at soil temperatures and moisture, soil temperatures there on the left, we see consistent with the air temperatures we've been talking about. Soil temperatures also have been generally above normal across much of the region, especially across Florida, southern Alabama, and Georgia, coastal Carolinas, near normal across the interior of the region where it hasn't been quite as warm. If we look at soil moisture there on the right, a lot of spotty dryness. So this is kind of typical during the summer. We see some areas where it's been fairly wet, where soil moisture is doing fairly well. Other areas where it's really beginning to dry out, especially across parts of southern Alabama, eastern portions of the Carolinas and Virginia, as well as the west coast of Florida. Okay, next slide. Okay, so looking at growing degree days, looking at the growing degree day accumulations there for the past 30 days there on the left, generally near historical averages for most of the region, except where it's been exceptionally warm, which is Florida, also parts of South Georgia. So similar story to what we saw last month. If you look there for one particular station there near Gainesville, Florida, there on the right, shows the accumulated growing degree days there through the season. As we talked about before, after a pretty warm winter, we got cool during the spring. That kind of led to a slow start to the season, but with the warmth that we've had here over the last couple months, growing degree days have really been able to catch up, and we see that again across a good part of the southern tier of the region. Okay, next slide. One impact here, this is actually from Dave Zierden, who added this. This is becoming an issue here across parts of South Georgia and North Florida, where we grow a lot of peanuts. We're at the time of year where water use by peanuts, or at least the water demand by peanuts is fairly high. We're looking here at several months after planting. And so, you know, again, we're at a point where water use is high, or water demand is high, and you can see this is in a part of the region where we've been rather dry over the last several weeks to last month or so. That's reflected there in the low precipitation that we've seen here over the last month or so there from climate perspectives there in the upper right, and then the AHIPS map there down there on the bottom showing over the last couple weeks a relatively dry pattern. So that could potentially impact peanuts and other crops across the region moving forward. However, if we go to the next slide, it should be the 7-day QPF, which we showed earlier. We highlighted the fact that this region from about North Florida up the East Coast could see, in some cases, maybe half an inch to an inch of rain over the next week or so, and that could certainly help improve moisture levels in this part of the region that you know, they could certainly use the moisture. Okay, next slide. Some observations from early harvest. So we've kind of reached the first phase of harvest here for the growing season. In places like South Carolina, we're done now with peaches and blueberries. And there was less frost there compared to places, say, like Georgia. So crops there are looking pretty good, as well as blackberries and other fruits. Summer vegetables are also doing well, even with the recent heat, but they're starting to tail off a bit. We're beginning to see the harvest of some varieties of wine grapes, including muscadines that are very popular in the Southeast. The harvesting of that has begun, but still need a few more weeks for those. As we mentioned, the early planted corn looks pretty good, but late planted corn really suffered from dry conditions at a critical growth stage, and so yields are likely to be lower there as we get later into the fall. Sweet potatoes looking good, and farmers, as you can imagine, this time of year, farmers are beginning to transition to their fall crops, and so we'll see how conditions over the next several weeks to months, especially with tropical activity, affects the planting of fall crops here moving forward. Okay, next slide. Okay, so there's the summary for you to look at after the webinar. And so with that, I'm going to pass it over to our guest speaker this month, Jacob LaFontaine, who's going to, again, talk about water availability, future water availability and streamflow characteristics in the Southeast U.S. Jacob, the floor is yours.
Excellent, thank you. Hopefully you can see the title slide from my screen. So I appreciate the opportunity to talk today a bit about some of the research that we've been doing in recent years with hydrologic modeling and the use of climate scenarios and downscale general circulation models, and seeing what effects those have as we look to hydrologic simulations with those types of forcings. So an outline just to give you a historical context and some of the literature and perhaps some of the changes that are already being seen, let alone what we're thinking about, you know, what the models are telling us, say, multi-decades out could possibly look like. Briefly go over our modeling approach for using this chain of inputs of climatological forcings through our modeling structure, and then looking at some post-processing to look at some example results for the Southeast region at a couple different scales. And then connections to broader work that is actually ongoing or ramping up within the USGS at the national scale. And then a key takeaway as we see some of the results and, you know, things to consider in using some of the information. So for historical context, Darren Carlisle and others had published a paper a few years ago looking at various stream gauges across the country that were considered reference gauges, where that definition being that, you know, they're minimally impacted by anthropogenic effects such as, say, urbanization or water use or flow regulations such as dams and reservoirs. And what they found is that looking at the timing of high flows being able to only consider the climate signal that for the Southeast, kind of along the Gulf Coast, there's perhaps some minimal change, but then in the two ecoregions that primarily cover most of the Southeast United States, that seeing a shift of the high flows from spring to winter. And so we start to think as some of these seasonal shifts happen, what that could mean for downstream effects or other responses to stream flow. When they also looked at not only high flows but low flows and looking at different stream flow characteristics, so you think of magnitude as the size of the flows that are occurring, the frequency is how often do those levels of stream flow occur, and then the duration when you have a lower high event, how long are they lasting. And so what we saw is in this in these top three panels that we see on the top left, that there's this group in the coastal plain and that darker tan area, that the red triangle is pointing downward, saying that generally they're looking at a decrease in low flows, in the Panhandle, Florida, South Georgia, up into some of the coastal plain in the Carolinas, and then on that top right panel, looking at along with those decreased magnitudes of flows, that perhaps there is also this increasing duration. So these the dark blue triangles pointing upward, saying that in conjunction with perhaps low flows, that we may be seeing those low flow periods last longer. And then when you look at the middle panels, that the green dots represent less than a 20% change, is that so perhaps if the magnitude and the duration are changing, but maybe there's a similar number of events that they've seen. So from using measured stream flow data that have occurred for decades to over a century in some places across the United States in our stream gauge network, this research I'm talking about today is taking a model-based approach, of which really does depend on the observation networks for us to be able to calibrate and evaluate our models. But we look to provide this consistent baseline information about hydrologic response, and what could the potential changes look like in the future by forcings such as climate or land cover. And so this research and these model outputs could look to supplement those stream gauge networks at, say, ungauged locations where we may have over 8,000 active stream gauges, but maybe you need information at a particular location or stream reach where we don't have an actual stream gauge. Allowing us to look at quantifying not only the direction but the magnitude of the potential changes into the future, looking multi-decades out using these modeling approaches, and how that could lead to how do we plan for future conditions and challenges, as well as identifying the needs for improvements with our methods. So hydrologic models, they can be useful for depending on your question you're looking to ask, but it may be that certain other processes that we don't currently represent within these simulations would need to be added to really get something more useful for managers or other folks. So this approach primarily uses this automated methodology that we've developed to scale up these large scale hydrologic models to really get at outputs of water budget terms, primarily stream flow. We've also recently added a module to our modeling structure to look at stream temperature information and simulating stream temperature. And so that'll be kind of a follow-on product to some of the results I show here today. So within USGS, this National Hydrologic Model infrastructure, we had started developing several years ago. And what we found is that as folks were developing individual models across the country, that because they were using different methods and different data sets, that they weren't really compatible when we were trying to look at what are potential changes in climate in the future. And so the NHM infrastructure is really meant to be this consistent underlying set of codes and spatial fabric and modeling units that we could simulate across the country in a consistent way and be able to cross compare. So there's three primary components. There's the actual physical modeling codes. There are the spatial units of which we parameterize our models or actually run the models on those units. And then there's the input data of, say, precipitation and temperature, which are typical forcings or inputs to these types of hydrologic models. So the model that we currently use, it's a USGS developed code. I think the first version of it was back in 1983, but it's gone through several iterations over the decades. So we're up to version 5 of the PRMS modeling system. So this is it's a deterministic model. So if you give certain inputs, it will give you a certain answer as opposed to a range of answers. The parameters are distributed across the landscape. It's based on physical processes. So if they're just relationships between certain physical processes, those are part of what the model simulation code does. And it runs at a daily time step. And so each with inputs of precipitation and temperature on a daily basis, the effects move through the various components of the model. So each of these boxes represents a different process within the hydrologic cycle that the model tracks and tracks the fluxes or the movement of water between these boxes, and then eventually out to the right here where you see that there's different components of flow that make up total stream flow. So the underlying spatial modeling units, building at this scale and at the time we did, it's based off the National Hydrography Data Networks, or NHD+, which a lot of national scale modeling efforts are currently using. And so the spatial modeling units across the country, what we've done is an aggregation of those to make something that's functional, that we can actually run efficiently. So the native data set has over 2 million of these polygons and catchments across the country. And for our application, based on where we had stream gauges, where there were reservoirs, where there were confluences between streams and rivers, it aggregated up to about 110,000 of these modeling units across the country. So that's on about a HUC12 scale, even though they're not the actual HUC12s across the country, but just to give a frame of reference. And it's also connected by a stream network of about 56,000 stream segments to route the water off the landscape units and out of the basins. So the third piece is the climate forcings. And so what we've done is we've calibrated, run our model and calibrated with this observation-based data set, or what we call this MAUR data set. So that actually took weather station data and then interpolated and extrapolated on a regular grid. So it took all those points and made a 12-kilometer gridded resolution across the conterminous United States. And so part of these studies that the Intergovernmental Panel for Climate Change runs, and they have different versions of these coupled model intercomparison projects. And so phase 5 is the one that is largely used now. Phase 6 has just recently come out, and folks are starting to work with the version 6 outputs. But for this study, we essentially looked at, there's 13 different global climate models that were then bias adjusted and made to the same grid resolution as this observation-based data set. And they have a historical training period as well as future time series out to the year 2100. So we took all of these different data sets. There's 62 different versions between the one observation based data set, the 13 historical GCM based, and then the 48 future scenarios, and run those all through the model, and then look at the range of outputs of the hydrologic cycle. And so what happens is when we get our final run of a model, then we can look at this, animation of, say, the observation. And so you can see that as precipitation comes in, it is partitioned into rainfall or snowfall if they're, in that type of part of the season, and seeing how then it perhaps moves into the groundwater system or contributes the different flow components, the fast surface runoff component or the slower like base flow component that you see when it's been dry for a while. And also looking at actual evapotranspiration and how in the bottom right, those all come together to give this time series of stream flow, and then also an example of stream temperature. So really looking at all of this level of information that comes out of these simulations, and how it can kind of be daunting when you start looking at the volumes of time series and file size coming out of these simulations. So when we aggregate that up and we look at these different representative concentration pathways, so the CMIP-5 study has 4 of these different RCPs, and so the 4.5, which is considered an average, middle of the road case, and then the 8.5, which is considered a high emission scenario that would have the effects on temperature and precipitation distribution out of those models. And so what we do is we take each of the ensemble of all the model runs for each particular RCP, and then look at, what are the extremes of those runs and say, what is the median? So this graphic just looks at projections of air temperature by season across the conterminous United States, and these are averaged around the 2045 to 2075 window. So we try to look at these projections in that kind of climatological time frame. What are the distributions across like a 30-year period? And so for the Southeast, you can see that not only does it matter which of these scenarios you look at into the future, but there's also seasonal differences across, just for one particular RCP. So if we look at the RCP 8.5, and looking at the temperature, range, it looks like, in this bottom middle panel, you can see that the projections of our air temperature will change by a lot more, say in the north central United States than perhaps in the southeastern United States. But that we do see seasonal differences. So like the RCP 4.5, that second row, that we see that perhaps summer temperatures and spring temperatures may change more than the winter temperatures, which are these cooler colors on the left and the right columns. As far as projections of precipitation, these tend to be have a larger range around them and what comes out of each of the different global climate models and the scenarios. But if you look at the RCP 8.5 across the bottom row, we definitely see that there's potentially some seasonal shifts in precipitation where and that the one that's labeled O on the bottom for the summer, it looked like perhaps there would be increases in precipitation projected in the future, but in the same time, the spring perhaps looks like for much of the region it could be somewhat less precipitation. And you see some of this play out in the annual averaged results as to that, perhaps there's not a total volume change, but it's the seasonality shifts that may matter. So just looking in the Southeast region, so these are the states and the HUC4 basin boundaries in the region that I've summarized some of the results to. So when we look at the Altamaha and the St. Mary's, so that's primarily in Georgia and central Georgia, and you look at these two different scenarios, so the middle of the road is the top table and the higher emissions is the bottom table. We look at what's the historical average temperature, precipitation, inputs, actual evapotranspiration, and streamflow values. And then the right three columns really look at across like the 13 runs into the future for that 4.5 scenario, what's the median, that percent change that we would see, as well as what are the kind of the outer limits. So for RCP 4.5 for that basin, it looks like, okay, maybe about +3 degrees Fahrenheit. Precipitation, maybe that's going to be around the same volume, but the range could be, plus or minus 10% on that volume. Actual evapotranspiration showing somewhat of a similar range. And then looking at the ratio of future stream flow to historical, we see that with that same amount of precipitation, but warmer temperatures and perhaps more AET, we're perhaps seeing a reduction in stream flow availability. And that's a similar story here with the RCP 8.5, but perhaps, with an increase of 5 degrees Fahrenheit, and then having similar precipitation volume, and looking at what are the range of conditions of potential stream flow. The future work could be about 17% higher, but it could also be down to one of the scenarios. So it was that 0.72 represents about minus 28%. So that's kind of the message we're getting at, is how to take all of this in context, and that we have a median value, realizing that the models really do represent a range of potential conditions. So looking at the Cumberland River HUC4, which is mostly in Tennessee, we see that the temperature changes are large, potentially larger than we see in the Altamaha, and that the actual evapotranspiration, where it was 1.05, is 1.09 potentially. So almost a 10% increase in actual evapotranspiration that could lead to further reduced stream flows as a result of having maybe a similar volume precipitation occurring. So looking at the basin scale in that way, and then just give you a couple of examples of how we can drill down into at stream gauge locations or stream reach out of these data sets. So there was a subset of stream gauges in North Carolina that we looked at, and these are primarily free of anthropogenic effects, again, so trying to isolate the climate signal. And what we see here is in the Blue Ridge for this site, Bee Tree Creek near Swannanoa, North Carolina, is that we look at this flow duration curve. So this is the distribution of flows over a 30-year time period. And we see that, you know, the black line is the historical time series of flows. And then the orange is that middle of the road, the 4.5 scenario, and the red is the high emission scenario. So for this site, we see that maybe the higher flows in the basin are going to be around the same general magnitude, but then once you get towards the right hand, and that's where the lower flows, we see that, okay, that maybe we're looking at low flows for not only the middle of the road emission scenario, but then even further reduced for the higher emission scenario. And so on the left here, briefly, just to talk about what that looks like on a monthly, kind of a mean monthly basis, and where the changes are perhaps occurring. So these top plots to the left are kind of these mean monthly flows, where the black is observations, the blue is the middle of the road, and the red is the high emission scenario. And on the right hand, for stream flow, precipitation, and actual ET, we look at what is the monthly ratio compared to the historical time series. So anything that's below the black line is considered a reduction. So, you know, perhaps a reduction in these flows from the April to the October time frame. In this middle panel on the right, we see, well, stream flow may be, or precipitation may be a bit higher, but not as, you know, but it does still stay kind of consistently near the historical line. But then the actual ET ratio on the bottom right panel, where we're seeing increased actual evapotranspiration really across the year, and maybe more drastically in those winter months. And so for another site where the previous site was just the lowest flows that were affected, when we look at this site, it seems like all but perhaps just the highest flow days, that there may be a general reduction in stream flow on the right, where, you know, from kind of the 5th percentile on the left here, all the way through to the lowest of flows. And so that's why, even though they're still in the same state, still in the same region, that really looking at this level of resolution to say, okay, everything's not going to generally change perhaps in one direction, but it matters where you are and kind of the hydrologic configuration of the area. And so for this one, we see that, you know, stream flow on the top right is generally reduced for both of the emission scenarios. The middle right, the precipitation, it looks like, you know, potentially have wetter summers, but then in the bottom right, we see that, well, that kind of comes along with, there may be more actual evapotranspiration that doesn't really allow that to really increase stream flows or buffer them. So just to connect to the broader work that is going on with USGS, is that there's these integrated water availability assessments that we're doing as a part of the Secure Water Act. And so we're looking at these at the national level, at the regional level, and in this national water census is really looking to be the delivery mechanism of the modeled outputs that we would use in those water availability assessments. So at a minimum, I would say you would think of the National Water Census as an interface somewhat similar to NWIS, but for modeled outputs instead of measured data. And really looking to quantify, you know, what's the historical and current and potential future water quantity, quality, and use across the country, what long-term trends, looking at long-term projections, and then trying to assess potential vulnerability. You know, what are the impacts on humans and ecosystems? So really the key takeaway in all this information is that when you start to look at the ranges of potential conditions in the future, you know, and folks say, what can I do with this, when it says, okay, precipitation could be the same, but it could also be plus or minus 30%. You know, it's like trying to find ways that within that range, still looking to find meaningful ways to use the information. You know, can you take particular scenarios, or what do those upper and lower bounds really mean in the context of the decisions that you're making? And so considering, again, that, you know, that range, is it acceptable? Does it change the decisions that we've made? And what can we do to further refine the applications we've done to make that information more usable? So I just want to thank everyone for your time. We've had several folks over the years that have collaborated and provided input on this, the funding from the Southeast Cast, from the Gulf Coastal Plains and Ozarks LCC, as well as the USGS Water Availability and Use Science Program. And I thank you for your time.
That is great. Thank you so much, Jacob, for your this presentation. We know how challenging it is to look ahead with the uncertainty, but it's really important for us to start assessing what the future will look like. Hello, everyone. Good morning. My name is Meredith Muth. I work for NOAA's NIDIS program, National Integrated Drought Information System, and we co-organize this 3-year running climate webinar series with the Southeast Regional Climate Center and with the National Weather Service. Just a reminder, if you have any questions for our speakers today, please enter them into the question box and we'll take them right now. Also, just a quick reminder that a summary, a recap of this webinar, as well as a link to the recording, will be shared with all of you later today or tomorrow. Please feel free to share those with your networks. Our next webinar will be focusing on climate-driven changes in prescribed fire in the Southeast U.S. So we'll make sure you have that registration link. And also just a reminder, we are always looking for comments on how to improve this webinar series. So before you leave today, a quick survey will come up. Feel free to fill it out, just a couple of questions, and let us know what you would like to hear about in future presentations and webinars. And so now with our last 10 to 15 minutes or so, we'll go ahead and take a few questions. Jacob, the first question is for you. It is asking you to please define interflow and lateral flow.
Okay, in the PRMS model structure, there's essentially 3 buckets, from the upper soil zone to then the subsurface reservoir that's not in the upper soil zone and not in, say, the saturated level where groundwater is. And so we have 3 tanks of water that account, and then each provide a flow component. So there's a kind of the fast surface runoff, and then the interflow is what would come from that lower zone above the saturated zone, where you would say get base flow generated. And that's just the things that are tracked out of the model. And then the lateral flow is the total of those 3 components that come off of the landscape and then get fed into the stream network and then get routed downstream.
Thank you, Jacob, for that clarification. The next question is going to, I think I'll put this over to Chris, but anybody can respond to this. That's any of our speakers. This is related to atmospheric rivers. So California has had 31 atmospheric rivers for this for the winters of October to spring, this last winter. And now with El Nino being linked to why there are so many atmospheric rivers. So because the Atlantic is warming as well, do we anticipate that the Southeast will experience atmospheric rivers? I think I'll just leave it at that. Or does the tropical storm hurricane reporting cover this?
This is Chris. Yeah, I'll start off. Over the last probably decade or so, there's been, or maybe even less than that, there's been some more research into atmospheric rivers in the Southeast. I know folks at the University of Georgia and other places have been looking into this. As far as links with El Nino, my understanding is, at least on the West Coast, El Nino plays a role in the strength of the rivers, not necessarily in the frequency or duration of those. And of course, there's other things going on, like the Pacific North American Oscillation, or the Pacific North American pattern and the Arctic Oscillation, that can sort of set up the circulation in such a way that atmospheric rivers would be more frequent there. What the large-scale patterns are that would influence atmospheric rivers in the Southeast, I think that's still an area of ongoing research. But there may be other folks that have some more insight into that.
Great, thanks, Chris. Next couple of questions is for Jacob. The first question is, how was actual ET determined in individual stream flow areas?
Sure. So on each of the those catchment areas, or what we call hydrologic response units that are across the landscape that this configuration has about 110,000 of, on each of those, all of those different water budget components are computed. And so for actual evapotranspiration, it depends on how much water is currently in the soil zone or in the canopy or in surface water bodies across the landscape. And then based on the capacity and the current status of those, then the internal equations compute, we compute potential evapotranspiration. And so then staying within those bounds, look at how much water is available on any daily time step to come out of those different storages in the model application. And so those are summed up on each of the hydrologic response units. And then for a particular basin above a stream gauge, those are all aggregated or area weighted to get a basin average above a particular stream gauge.
Great, thank you. Okay, Jacob, don't leave. I got a couple more for you. When can we review the results of the analysis that was summarized in your presentation for particular watersheds of interest?
So I'm happy to say, as of yesterday, the data release that will be hosted on ScienceBase was approved for release. So we'll be going through that process like this week into next week at the latest. I would say that data release will be made public, and then there are various output files of Streamflow. There are already pre-computed statistics of Streamflow for each of the stream segments across the country, and then we also included the input files that would be needed to recreate those. So there should be ranging levels of pre-computed information, or if folks want to regenerate or output more variables that the PRMS is able to, that should be available very, very soon. So that's been a long thing in the making. And so, yeah, I just saw the email come through yesterday that it's been approved for release. So we're going to move on that as soon as we can.
Well, that's fantastic. Congratulations. And yeah, we'll make sure that once that release is official, we'll also share it with this webinar community. And I don't have any other questions right now. Any last comments from our presenters? You're welcome to share. Okay, and then with that, I'd like to again extend my heartfelt thanks to our guest presenter, Jacob, as well as our regular presenters, Jeff, Chris, and Pam, who couldn't join us today. And with that, I wish you all a wonderful day, and we'll see you next month. Thank you.